Hello, we are covering exponential functions in this video, broken up into two parts. So this is part one, exponential functions. Actually, this is 4.1, exponential functions. Adding to your list of functions. Okay, so what is an exponential function? Okay, so the exponential function with base A is defined for all real numbers x by the following: f of x, which equals a to the x. Okay, so in previous functions, you were used to seeing numbers for the exponents. But now for an exponential function, we see that the exponent has a variable. Okay. And our conditions here, where a is greater than 0 and a is not equal to 1. All right, so let's take a look at a few examples here. So you might have something like this: f of x equals 2 to the x. That's an exponential function. You might have g of x equals 3 to the x. Okay. You might have h of x equals 10 to the x. Okay. And evaluating, so when we're evaluating, remember we replace all the x's with whatever value it is that we are evaluating for. Okay, so let's take a look here. Okay, let's let f of x be 3 to the x. Evaluate the following. Okay, so if we wanted to find f of 5, then we would need to replace the x value, which is here. Replace the x value with 5. Okay, so this would be 3 to the 5th power. Okay, and if you plug that into your calculator, make sure you do it correctly. You should, if you have a calculator, you would do this, and your exponent button is most likely that button, or the y to the x button. So it might be that one, or you might have a button that looks like that. Most modern calculators have this one over here. Okay, but make sure you are able to punch this into your calculator. So you would punch it in like this, and your equals 243. Okay. Suppose you wanted to evaluate f of negative 2/3. Okay. So if you punch this into your calculator, 3 to the negative 2/3, Go ahead and punch that in your calculator because sometimes students will get this wrong. Okay, so it's important that you are doing it correctly. So punch this one into your calculator. If you don't have a calculator with you, use your phone. Turn it sideways. If you go to your calculator function, and if you turn it sideways, then you have a scientific calculator. Okay. Turn it sideways, and you should see, depending what kind of phone you have, you will see this button for the exponent, or you will see this button for the exponent. Okay. So go ahead and punch this in and see if you get this answer. See if you get this. 0.4807498. Okay. If you don't get this answer, then check to make sure that you did parentheses around -2/3. Okay. So when you're punching this into your calculator, this is what it would look like. 3, and then your exponent button, whichever one that is that you have. And then you would actually use a parenthesis button. Okay. And then 2, and then your division button, and then close your parentheses, and then hit equals. Okay. And then see if you get it. Okay. So just make sure, because we're getting into exponentials, and I would say most of the time students miss these problems on the test because they entered it incorrectly on the calculator. Because when they show their work and I watch their work, everything's correct except the final answer. Okay. All right. F of pi. So you would do 3 to the power pi. Okay. Check to see if you get 31.5442807. Okay. And f of square root 2. Okay. So that would be 3 to the square root 2. And check to see if you're able to get 4.7288043. Okay. All right. So let's do some graphing. All right. So suppose that we want to graph f of x equals 3 to the x. Okay. So one thing you want to notice here with exponentials is that no matter what I plug in here for x, no matter what I plug in, whether I plug in 0 or a positive number or a negative number or a fraction or a negative fraction or a very big number or a very negative number, no matter what I plug in here, my result, the answer that I get, will never be 0. Okay, so it'll never get to 0. And it will never be negative here. No matter what I make this exponent, the result will never be a negative outcome. Okay, and it will never be 0. So that affects the way our graph is going to look. All right, so if I make a table of values here, you can say f of x. If you're used to y, then use y. All right, so when x is 0, okay, then over here, let's just go ahead and do this in our heads. 3 to the 0 is 1. Okay. And when x is 1, okay, 3 to the first power is 3. And let's just go ahead and do one more here, -1. 3 to the -1 power. Remember, when you have negative exponents, you have to take the reciprocal. So it becomes 1 over 3. Okay. And let's take a look at what we have here. Okay, so we already said that we will never have a negative outcome. So that means we're never going to be down here. Okay. And there's no way to get 0. So we're not going to cross the x-axis. Okay. That means our graph is going to be up above here, somewhere up here. Okay. All right. So let's go ahead and plot these points. 0, 1, 1, 3, -1, 1/3. Okay, so what happens here is, again, this will never cross the x-axis, okay, because there's no way to get 0. There's no way to get negative numbers, so we're never going to be down here, and we're not going to cross this, okay? So what happens is we're going to get a graph that looks like this, very close to the x-axis, and then goes up. And we could see that because, watch, if I plug in 2, then I get 9. And then when I plug in 3, I get 27. So already here, I'm at way up at 27. When I get to 3, I'm way up here somewhere, okay? Which is why I didn't choose 3, okay? But this is the basic graph of an exponential. Okay. So go ahead and try graphing this. Okay, making your table of values here. Okay, go ahead and what are good values to choose? 0 is good, 1's good, -1. Those 3 are my favorite, but you can always choose whatever you want. All right, go ahead and plot this one and see if you get the same thing that I do. Okay, so here, when x is 0, 1/3 to the 0 power is 1. When x is 1, plug in 1, 1/3 to the first power is 1/3. And then -1, when x is -1, I take the reciprocal, so it's going to be 3 over 1. But 3 over 1 is the same as 3. Okay? So when you graph this, still the same as up above. No matter what I plug in here for x, we are never going to get a negative result. So we're not going to be down here with our graph. And no matter what I plug in for x, there is no way to get 0 here. So I'm not going to cross this x-axis either. Okay? So again, this graph will be somewhere above here. Okay? So I have a point at 0, 1, 1, 1/3, -1, 3. Okay? So it looks very similar to the other one, except it's kind of going in the other direction. Okay? So we see here, we had 3 to the x, and our graph was increasing from left to right. This is exponential growth. And over here, we had 1/3 to the x, and our graph was decreasing from left to right. So we have growth over here, exponential growth, and here we have exponential decay. Okay, and so if we take a look here, if we compare these, if we inspect this here, it turns out that we'll have exponential growth if the base here is greater than 1. Okay, if this is greater than 1. Over here, we will have exponential decay if we have this fraction here between 0 and 1. Because remember, fractions exist outside of 1, right? Beyond 1. So this is a number somewhere between 0 and 1, a fraction number between 0 and 1. Okay? That's when you'll have this decay. All right, so let's write that down. So in general, if f of x equals a to the x, and a is greater than 0, and a is not equal to 1, then the domain will be all real numbers. Okay. If you want to use set interval notation, okay, so negative infinity to positive infinity, and the range, those are our y values. We see that we're not going to be 0. We're going to be everything greater than 0. So not a bracket, but parentheses, 0 to infinity. Okay. And if a is greater than 1, then we'll have exponential growth. Okay. So we will have that. Okay. Where this is 1. Okay. So it is increasing. And we call this exponential growth. Okay. If a is between 0 and 1, then we have exponential decay. Again, that's at 1. So our function is decreasing here, and we call this exponential decay. All right, so identifying graphs. So let's look at an example here. Find the exponential function whose graph is given by. So find the exponential function whose graph is given by. So I'll do one, and then I'll give you one to do. By this. Okay. And let's suppose that over here you have this point on the graph, which is 2, 25. Okay. So you can kind of guess, you can probably tell intuitively what that's going to be. Okay. So we're trying to find an equation. We're trying to find an equation that looks like this, right? And we want to find out the base. So that's what we're really trying to find. We want to find the base. Okay. So if you can't tell what that is just by observing there, then plug in this x and y value here. Okay, so you have this x and y value right here. So if you can't tell that the base is 5, then use that x and y value. And then maybe you'll be able to see it when it's written like this, in this form. A squared equals 25. Oh, a must be 5, right? Okay, so then that would be your function. F of x equals 5 to the x. Okay? All right, go ahead and see if you can find the function for this one. Okay? suppose that you have a decreasing function. So that tells you something about the base. Okay, and then suppose that over here you have this point, and this point is 3 comma 1/8. Okay, go ahead and see if you can find the function. Go ahead and hit the pause button. Okay, so again, if you can't tell, then just do this. Plug in 1/8 for y and 3 for x, and then maybe you can see it this way. So that must be um, that must be 1/2. Okay. Now, if you're looking at this guy, I can't see how you got 1/2. Another way, once you set up like this, if you feel like you need some sort of process for doing this instead of intuition, okay, and by looking at this, if it's not obvious to you, then you go ahead and solve for a. You can solve for a. You have to get rid of that cube, right? If you can't see that it's 1/2, then go ahead and take the cube root of both sides. If you take the cube root of both sides, right, then hopefully there you can see that a is 1/2. Okay. I'm kind of hoping you'll be able to see it right off the bat when you look right here. Okay. But if you can't, that's not a problem. Then go through the process of solving like we did here. Okay. So here is your function. Okay, so let's take a look at transformations, the shifting when we're graphing. Okay, so you're given a parent function. Okay, and your parent function has this form, some base to the x power. Okay, and so you will be shifting up or down, depending on positive or negative. If it looks something like this. So if it's plus c, then you'll shift up. If it's minus c, then you'll shift down. Okay. And then you'll shift just like our previous functions. Shift left, right. So your function would be the parent function, but you're adding or subtracting to the x value now. Okay, so x plus c shifts it to the left. X minus c shifts it to the right. Okay? So let's take a look at some examples. Let's go ahead and graph g of x, which equals to 1 plus 2 to the x. Okay? So here, whether it's written as 1 plus 2 to the x or 2 to the x plus 1, it's the same. So hopefully you recognize this as a shift up. Okay? All right, so the parent function, which is f of x equals 2 to the x. If you make a table of values for that, 0, 2 to the 0 is 1. 1, 2 to the first is 2. Negative 1, 2 to the negative 1 is 1/2. Okay, so then we're going to take the parent function and graph it. 0, 1, 1, 2, negative 1, 1/2. Okay, so this is our parent function. Here, I'll do kind of a dotted. Okay, and then we're going to shift this all up 1. So here, you know what? Yeah, that's okay. we shift all three of these points will get shifted up one. So this point goes up one, this point goes up one, and this point goes up one. And this axis that never gets crossed also shifts up one. Okay, so you can, here, let me do it in red, and actually let me do it in a highlight, and let me do it kind of bigger. Okay, so like right here we have this sort of asymptote, you can think of it. Okay, and that is also going to get shifted up one. Okay, so now it's going to go up here. Let me do the final one in purple. Okay, so it gets shifted here up one. Okay, and then our graph is this one right over here. Okay, all right, let's take a look at another one. All right, so let's go ahead and take a look at this graph. H of x equals -2 to the x. Okay, so if you remember here, this multiplies the original y values. This is going to reflect it, right? This is going to reflect it over the x-axis. Okay, so let's do our parent function. F of x equals 2 to the x. When x is 0, y is 1. When x is 1, y is 2. If you want to do one more, that's fine. We get 1/2. All right, so parent function 0, 1, 1, 2, -1, 1/2. This is our parent function. Okay, multiply all the original y values. So this one, y value becomes -1, or actually 2, -2. Let me do that over. Okay, so this y value here is 2. So if I multiply by -1, it flips. This has a y value of 1. So if I multiply by -1, I get -1. This one has a y value of 1/2. So multiply by -1, and I get -1/2. Okay, and so we can see that it's a reflection over the x-axis. To me, sometimes when it's written like this, it's almost more work to do it this method. I think I would just go ahead and make a table for this one, instead of making a table for the parent function and then doing this here. Okay, it'll be up to you. I think this understanding it will be helpful when they ask you in the homework questions like, what happens to this graph when you do this? Then you have to say, oh, you get a reflection over the x-axis. Okay. All right. Oops, sorry, that's my kitty cat. Okay. All right, let's take a look at this one. Let's go ahead and graph k of x, which equals 2, 2, to the x minus 1. Okay, so now the x is subtracting 1, so that's going to be a shift left or right. Okay, so over here, because this is -1, it's going to shift 1 unit right. Okay, so again, our parent function is f of x equals 2 to the x. And we already know that we get when x is 0, y is 1. When x is 1, we get 2. -1, we get 1/2. Okay, so when we graph this, our parent function, 0, 1, 1, 2, -1, 1/2. We keep seeing this same graph. Okay, and now it's going to take all three of these points, and we're going to shift them all 1 to the right. So this one goes 1 to the right, this goes 1 to the right, and this goes 1 to the right. And then our graph looks like this. Okay. All right. So all the shifting still is the same as other functions. Okay. All right, let's take a look at comparing exponential and power functions. Comparing exponential and power functions. All right, so let's go ahead and consider the following. Suppose that we have this here, f of x, which equals 2 to the x. This one's an exponential function, right? And then let's compare that with g of x, which equals x squared. This one is a power function. Okay. And let's take a look. So if you have a graphing calculator, you can take a look at these two graphs, graph them in the same viewing windows. But I know not all of you guys have a graphing calculator, but you could also probably find one online. Okay, so we're going to look at these two graphs with these viewing windows. Okay, so the first one, A, is going to be between 0 and 3 by 0, 8, 0 to 8. Okay. So when we look at this here, this is what the graph looks like. Okay. So what happens is you have f of x. Okay. So f of x starts over here and goes like this. Okay. And g of x. So this one's f of x. And g of x starts over here and does this. And they intersect right over here at 2, 4. Okay. So this is what it looks like when you're looking at a viewing window from 0 to 8 and 0 to, here, I guess this is not really to scale, but zero to 3. Okay. So that's what we mean by this 0, 3. That's the range of the x values, and 0, 8, that's the range for the y values. Okay, so when we look at this tiny window here, it looks like, oh, wow, g of x, which is this one over here, it looks like, oh, wow, g of x is is increasing much faster. But and that's the power function, right? Okay, but let's take a look at a different viewing window. If we look at the viewing window x values from 0 to 6 by the y values 0 to 25, if we look at that window, then we have a more interesting thing happening here. Okay, and what happens is this might be our f of x function, right? And then this is our g of x function. And so what happens is before we were kind of looking at that function only like between here and here, right? And so it looked like the g function was increasing much faster, right? Because we're only looking at it from this window, right? But then we look here. So here we said it was crossing at 2, 4. This other place that they're crossing is at 416. But then here, afterwards, f of x, the exponential, just keeps on increasing at a much faster rate. Because this here, g of x just kind of gets wider and wider and wider, while this just goes almost vertical. Okay. And if we look at this viewing window, if we look at the x values 0 to 20 by these y values 0 to 1,000, then here, then you can't really see those tiny things that are happening there, because it just kind of looks like this. That's f of x, and this is g of x. Okay, but that's y values from 0 to 1,000. Okay, so it's really interesting because if you zoom in to these little areas, this is what's happening over there. But the overall behavior, f of x, the exponential function, is increasing more quickly. Okay, so that is all of part 1. So if you have any questions, make sure you message me or you email me. I respond much more quickly to your text messages via the Remind app than I do with the emails. Okay, I will see you for part 2 in a bit.